Welcome back, everyone, to another deep dive. Today, we're tackling something pretty foundational and I think especially useful, no matter where you are in the AI world. We're going to be looking closely at Clause 8 of the ISO IEC 22989.2022 standard. And, for anyone really who's interacting with AI, developing it, even just trying to keep up with all the news, this clause is like getting handed a detailed map of how it all works. We're going to break down this AI ecosystem piece by piece. So consider us your guides, maybe even your instructors for this exploration.
That's a great way to put it. We really want to take you through Clause 8 in a clear, step-by-step way, making sure these concepts, which can get pretty complex, are understandable for everyone. Not everyone's a computer scientist.
Exactly. So looking at our map here, Clause 8, what are the main landmarks we're going to hit? Well, it starts with a broad overview, the general AI ecosystem. Then it zooms in on individual AI system, what those actually look like. Then we'll dive into how these systems function, the core of what they do. Then we'll compare machine learning and predictional engineering approaches, sort of like two different toolboxes for building AI. We'll see how big data and all its sources, including cloud and edge computing, fit into this picture. And finally, we can't forget the resources, the fuel that powers this whole ecosystem.
That's the plan. We'll tackle all of that in that order, almost like we're taking a guided tour through the standard itself. So, ready to start with the general AI ecosystem, section 8.1.
Let's go.
Okay, so 8.1 kicks things off with this idea of an AI ecosystem. And luckily, we've got a visual aid. Figure 6 in the standard shows us a diagram of it. Now, what's interesting here is that when you look at large AI systems, the kind that are doing some really impressive things today, well, they're not usually built on just one shiny new technology.
So it's not like one magic bullet that makes all the AI happen.
Right, exactly. It's more like a blend of different approaches that have been developed over time. So you might have neural networks working alongside, let's say, symbolic models or even probabilistic reasoning, all within the same system.
Like a team of specialists, each with their own strength.
That's a great analogy. And this layering, this modular approach, it's powerful, but it also means you have to be mindful of how these layers interact. An issue in a lower layer, sort of a foundational piece, can ripple upwards and affect the whole system. So reliability is a key thing to consider here.
That makes a lot of sense. Like if the foundation's shaky, the whole structure's at risk. And the standard also talks about this as a functional view, with each layer depending on the layers beneath it.
You got it. But here's a point the standard makes very clear. The size of those layers in the diagram, or even the individual components they show, doesn't necessarily reflect their importance.
Oh, interesting. So it's not a hierarchy of importance, but more about how they connect.
Exactly. It's about the relationships and dependencies within this ecosystem.
Makes sense. And another thing the standard emphasizes is that creating AI systems, this whole field, it's not a finished puzzle. It's still a very active research area. There's a lot we're still figuring out and improving upon.
Absolutely. We're learning new things all the time, developing new techniques. And at the same time, the use of AI is booming across so many industries, from healthcare to finance, transportation, manufacturing. Each sector has its own specific needs, its values, and of course, legal boundaries it has to operate within.
So that diversity, the different ways AI is being used, that shapes the ecosystem itself, right?
You got it. It drives the need for more specialized AI systems, those tailored to specific tasks and challenges. It also influences where research and development efforts are focused. We're seeing this trend towards specialized AI applications, and some really powerful ones have emerged.
Like what?
Well, take computer vision, for example. It's this amazing ability for machines to see and interpret images. Or natural language processing, which allows machines to understand human language. These are becoming fundamental building blocks, and they're being integrated into all sorts of products and services. Think about facial recognition on your phone, translation tools online, chatbots, they're everywhere.
Yeah, it's amazing how seamlessly some of that AI has become part of our daily lives.
It really is. But we can't talk about modern AI, especially the machine learning side, without acknowledging the sheer amount of resources it often requires.
You're talking about computing power, right?
Yeah.
Data storage.
Exactly. And network resources, too. Especially when you're training these AI models, it can be incredibly demanding.
So how do we handle that?
Well, that's where cloud computing comes in. It provides a way to access and scale those massive resources on demand. Think of it like a giant shared pool of computing power that you can tap into. It's become a cornerstone of modern AI development and deployment.
Okay, so we've got this general picture of the AI ecosystem. Now let's shift our focus to individual AI systems. Section 8.2, right?
Right. 8.2 reminds us just how diverse and adaptable AI systems are. They can be applied to a huge range of problems and designed to perform all sorts of tasks. If you're curious about specifics, Clause 9 delves into those application areas, and Clause 5 breaks down the types of tasks that AI can tackle.
And is there a sort of general path of flow that these AI systems tend to follow?
There is. It usually starts with information acquisition. This is how the system gathers the knowledge it needs. And this can happen in two main ways. Hard coding is one. That's where human engineers explicitly program the system with the knowledge it needs.
So kind of like writing a detailed instruction manual for the AI.
Exactly. But then there's the other way, machine learning. This is where the system learns from data, building its own internal model, its own understanding of the world.
So it's figuring things out on its own based on examples.
Precisely. And once it has that model, the system moves into a reasoning phase. This is where it applies what it knows, using its model to explore potential solutions or figure out what should happen next. And this reasoning can take many forms. You have spatial reasoning, like a robot understanding where objects are in a room. You have temporal reasoning, like predicting how traffic flow will change over time. And even common sense reasoning, knowing not to do something that's obviously a bad idea. Then you have reasoning based on applying predefined policies or rules. And finally, we get to the decision-making stage. This is where the system chooses a course of action based on criteria like user preferences or some calculated utility.
So from gathering information to processing it to acting on it. That makes sense. Now, Section 8.3 talks about the AI function. What's its role within this whole process?
So the AI function really comes into play after the model is built, either by humans or through learning. Its main job is to take that model and the relevant data and compute an output. This could be a prediction, like forecasting the weather. It could be a recommendation, like suggesting a product you might like. Or it could be a direct decision, like an autonomous system braking to avoid an obstacle.
So it's all about putting that model to work, using it to generate useful output.
Exactly. And we talked about reasoning earlier. Well, the AI function handles this too. Reasoning, in this context, means applying the data for the current situation to the model. It's like asking the model, okay, given what we know right now, what are the possibilities? What should happen next?
And what kind of tools are used for this reasoning?
The standard gives some great examples. Planning systems, figuring out sequences of actions to reach a goal, Bayesian reasoning, which uses probabilities to make inferences, automated theorem provers, using logic to prove statements, systems for spatial and temporal reasoning, which we already talked about, and ontology reasoners, AI that can understand the relationships between concepts, like how a car is a type of vehicle and has wheels. And importantly, machine learning itself can be seen as a way to implement certain types of reasoning.
Right. It's all about how the system processes information to understand the situation and figure out what to do. Now let's move on to Section 8.4, which is all about machine learning, a term we hear everywhere these days. How important is this in the bigger picture of AI?
Well, it's definitely a core element of many modern AI systems. Not every AI uses machine learning, but it's become incredibly widespread. The basic idea is to let systems learn from data without needing a human programmer to write out every single rule.
So instead of a detailed manual, it's learning by example.
Precisely. And the standard really highlights the importance of algorithms here. These are the sets of instructions that make this learning possible, allowing computers to learn from data and experiences. And the goal is often to create a model, a representation of what the system has learned, so it can make predictions or decisions when it encounters new, unseen data.
And I know there are different types of machine learning, right? Not just one size fits all.
Absolutely. Clause 5.11 gets into the nitty-gritty of it, but in Clause 8, the key thing is to understand the main categories. There's supervised learning, where you give the system labeled data, telling it what's what, like training an image classifier with pictures labeled cat or dog. Then there's unsupervised learning. This is more about finding hidden patterns in data that's not labeled, like grouping customers based on their behavior without knowing the categories beforehand.
So finding the connections without being told what to look for.
Exactly. Then you have semi-supervised learning, which uses a mix of both labeled and unlabeled data. And finally, there's reinforcement learning, where an AI agent learns by interacting with an environment and receiving rewards or penalties for its actions. It's like training a robot to navigate a maze through trial and error. Each of these types uses different data and learning techniques to achieve its goals.
And this machine learning process, it's not a one-time thing.
No, it's usually iterative. You train the model on a bunch of data, then you use a separate set of data called validation data to fine-tune it, prevent it from memorizing the training data too specifically. And finally, you test it on a completely independent data set to see how well it performs on new stuff it's never seen before. This whole cycle of training, validation, testing is key to making sure the model actually works in the real world.
Okay, that makes sense. So that's machine learning. Now let's switch gears to section 8.5, which focuses on engineering. This is the other toolbox, right? How does it differ from machine learning?
With engineering approaches, it's all about human expertise. Instead of the system learning from data, the knowledge is hard-coded, directly embedded in the system by the developers.
So it's taking what humans already know and putting it into the AI's code.
Exactly. And remember, we talked about different types of knowledge back in section 7.3. Well, those are at play here. There's declarative knowledge, which is all about what is. It's factual, easy to state, like the earth is round. Then there's procedural knowledge. This is more about how to do something, often harder to put into words, like riding a bike. You know how to do it, but explaining every balance adjustment is tough.
And then the standard talks about expert systems. What are those, and how do they fit into this engineering approach?
Expert systems are all about capturing the knowledge of human experts and using that to solve problems in a specific field. Imagine a system that can diagnose diseases based on doctors' expertise, or a system that helps engineers troubleshoot complex machinery.
So like having access to a top expert in your pocket.
That's the idea. And these systems usually have a few key parts. There's the knowledge base, which stores all the facts and rules, the declarative knowledge. Then there's the inference engine, which handles the procedural knowledge, the rules and methods for reasoning with that knowledge. And finally, there's a user interface so people can actually interact with the system.
And when you use an expert system, it's essentially following a set of rules to arrive at an answer.
Right. The inference engine takes the information you provide, combines it with the knowledge in its database, and uses logical evaluations to figure out a solution. They've been successfully used for things like classification, diagnosis, monitoring, and prediction.
Okay, so it's about encoding human expertise into a system. Now, the next part of the engineering section talks about logic programming. What's that all about?
Logic programming is a way of writing programs based on formal logic, with a language like Prolog being a common example. Now, formal logic has been a big area of research in AI. Different logics try to model how humans reason in different situations, and logic programming gives us a way to implement those models computationally.
So it's about making AI reason more like a human, following logical rules.
Exactly. And the standard points out that if you combine declarative statements, those facts, with strong natural language processing, logic programming can let an AI agent reason by analogy, draw conclusions, even make generalizations about the world. And they give an example, Apache Jenna, a semantic web framework that includes an inference engine. So these logical principles are actually being used in real systems.
That's fascinating. It's like teaching AI to think logically. Now let's shift gears again and talk about data. Section 8.6 covers big data and data sources, and also introduces cloud and edge computing. Data feels like the lifeblood of so much of AI, especially machine learning.
Absolutely. Data is the fuel, the raw material that many AI systems depend on. And Section 8.6.1 starts by talking about the role of data and how sometimes we're dealing with big data. Figure 7 in the standard gives a good visual of this. So what is big data? It's not just about having a lot of data, though that's part of it. It's about data sets that are so large and complex that traditional methods for handling them just don't cut it.
So what makes them so challenging?
Well, it's often described using the 4 V's: volume, variety, velocity, and variability. Volume's the easiest. That's just the sheer amount of data. Variety refers to the different types of data. You might have text, images, video, sensor readings all mixed together. Velocity is about how fast this data is coming in. Think of real-time streams of data from sensors or social media. And variability is about how much the data can change over time in its structure or content.
So it's a moving target, lots of different things coming in quickly and constantly evolving. No wonder traditional systems struggle with that.
Exactly, and that's why new technologies have emerged to deal with big data. Things like distributed processing frameworks that can spread the work across many computers, and specialized databases designed to handle these huge, diverse data sets. Big data is essential because it allows us to discover patterns and insights that would be impossible to find with smaller data sets. And for machine learning, it's crucial for training powerful models.
Okay, so we know big data is important, but where does it actually come from?
It can come from various sources. First-party data is collected directly by the organization using it, like a website tracking user behavior. Third-party data comes from external providers who collect and sell data, and often organizations combine their own data with third-party data to get a more complete picture.
And the types of data.
The standard lists quite a few: transaction records, surveys, sensor readings, images, audio, even just interactions people have with systems. It's really a wide range.
Now let's talk about cloud and edge computing.
Hmm.
Section 8.6.2 introduces these. How do they relate to big data and AI?
Well, cloud computing is all about accessing computing resources over a network. It's often associated with massive data centers that offer huge amounts of processing power and storage. Think of it like renting computing power instead of owning it.
So the cloud provides the muscle for handling big data and training AI models.
Precisely. Now, edge computing is a bit different. It's about doing processing closer to where the data is generated at the edge of the network. Think of sensors on a factory floor or in a self-driving car.
So instead of sending everything to the cloud, some of the work happens locally.
Right. This is often driven by the need for real-time responses, where sending data to the cloud and back would take too long. It also makes systems more resilient because they can keep functioning even if the network connection is interrupted. And importantly, edge computing can help protect data privacy because sensitive data doesn't have to be transmitted over the network.
So they both have their pros and cons.
And actually, the standard points out that cloud computing itself can be deployed in a distributed way, including closer to the edge, so it's not always a clear cut either.
Makes sense. Now let's move on to the final section. Section 8.7, which talks about resource pools. What are these and why are they important?
This section is all about the underlying infrastructure that makes the whole AI ecosystem possible. Resource pools are the computing power, networking, and storage that we need to build and run AI systems.
So the foundation that everything else is built on.
Exactly. And the standard emphasizes that AI systems operate at many different scales. You have those huge cloud services, traditional data centers, individual servers, edge devices, smartphones, even tiny IoT devices. And the processing power itself can come in various forms, different arrangements of GPUs, NPUs, CPUs, other specialized processors.
And the processing needs aren't all the same.
Right. Definitely not. It depends on whether you're using machine learning, deep learning, what kind of tasks the system is doing. Different types of neural networks, for example, have very different computational needs. And this often leads to using heterogeneous computing, where you use the best processor for each specific task. The standard even mentions hardware accelerators like GPUs, NPUs, FPGAs, DSPs, and ASICs, specialized chips designed to speed up those demanding AI tasks.
And how do we manage all these different resources?
That's where resource provisioning comes in. It's about allocating and managing those resources, often automatically. This includes getting resources on demand and coordinating them across different environments, like your own data center, the cloud, and edge devices.
Sounds complicated. And finally, we have application-specific integrated circuits, or ASICs. What are those?
An ASIC is a chip that's custom designed for a very specific purpose, and they've become a really powerful way to build dedicated AI capabilities. They can be designed as accelerators with specialized hardware to speed up specific AI tasks. They can also be coprocessors that handle specific parts of the AI workload, like image processing.
So they're super efficient, but only for very specific things.
Right. Compared to general-purpose chips, ASICs are designed for a particular scenario, like a certain type of neural network. They can be much faster and use less power, but they're not as flexible. The standard points out that ASICs are becoming really important for enabling AI in devices where space and power are limited, like smartphones and many IoT devices.
Wow, we've covered a lot, from the broad AI ecosystem to these super specialized chips. It's amazing how all these pieces fit together.
It is. We've seen how AI systems are built, how they function, the role of machine learning and engineering, the importance of data, and the crucial infrastructure that supports it all.
Understanding this framework, this map of the AI landscape, really is valuable for anyone who wants to understand this field.
Absolutely. It's foundational knowledge.
So as we wrap up our deep dive into the AI ecosystem, as laid out in Clause 8, here's a final thought to consider. Think about those different layers we talked about, from the apps we use every day to the hardware that powers them. How might changes in one layer, maybe a breakthrough or a bottleneck, affect the other layers in the future? It's an interconnected system. And understanding those connections is key to anticipating where AI is heading next.
And we encourage everyone to explore ISO IEC 22989.2022 in more detail. It's a great resource for anyone serious about understanding this field. Thanks for joining us for this deep dive, and we hope you'll tune in for future explorations into the fascinating world of AI.